So, first of all, we've hit a milestone. County regulations and UNL guidelines have always stated that lecturers, as long as they are vaccinated, of course, and at least 6 feet away during presentations, don't have to wear a mask. I've been doing so out of an abundance of caution because I've had two younger children at home who are not able to be vaccinated until recently. That changed on Saturday, and they received their first dose. So unless there are objections, and I will honor any request to put a mask back on during lectures, before and after, of course, I will be wearing it. But if you have any problems with that, make sure to post on Piazza, post on YouTube anonymously if you like. I will honor all those requests. But otherwise, hopefully by the end of the semester, or maybe even after Thanksgiving, we'll be out of a mask mandate entirely if we can get vaccination levels up. So if you haven't already and you are able to, make sure that you go out and get that. All right. I also had my booster a couple weeks ago, so I've actually had 3. All right. So we're starting on the last module, the last major part of this course. After we come back from Thanksgiving, of course, we'll be talking about graphical user interfaces and database stuff. That's kind of like the gravy. That's the extra stuff on top. This is the last major core topic of this course. And so it is going to take us the full 2 weeks here, maybe a little bit beyond if we want to do some more demonstrations. But it's algorithms, searching, and sorting. And why? Because data processing is a huge part of computer science. In fact, it's such a huge part that it's kind of grown off into its own little branch called data science, right? Whether or not that's necessary, right, is a debate. But fundamental operations to data processing are searching and sorting. And so that's what we're going to be focusing on now for the next 2 weeks. It forms the basis of a lot of other algorithms. Here's another algorithm, and before you even do this, you have to sort it, or you have to search something in order to execute this other algorithm over here. It's also a nice way of looking at data processing because there's a huge variety of algorithms that have been developed over the years. And with different efficiencies, different approaches, different properties. You might have seen, if you go to sortingalgorithms.com or something like that, or if you go to YouTube and look at sorting videos, there are a whole myriad of ways of visualizing how these algorithms work. All right. So before we get started, though, I want to show you a demonstration here on why this stuff matters. Okay. I just wrote this morning. This is a small program here that seeds a random number generator. It takes n as a command line argument here, and it generates an array of size n. So if I say I want an array of size 10, it'll give me a random array of size 10. If I say I want an array of size 1 billion, it'll give me an array of size 1 billion. Right? Then it goes through and finds the most common element here, and it reports what that element is and how many times it appeared. Okay? Ignore the stuff below here for now. So most common element, let's go ahead and take a look at what that looks like. Right? What it does is it establishes 2 loops here. So this outer loop here runs from I up to 0 up to n minus 1. And it assumes that, suppose that the ith element is the element that is the most common. What we're going to do is we're going to go through the array again and count up the number of times that it appears. Right? Say that 5 appears 10 times. All right, great. If that's more than 3 that only appeared 8 times, then what we do is we update our most common element, and we update the maximum count here, ultimately reporting what the maximum count was and what the most common element was. So let me go ahead and compile this and run it. Duplicates. Right. And we'll just run it on a small array. I'm not going to print out the array or anything like that. And it found that 215 was the most common element. It only appeared once. You can have elements that are all the most common elements. These are called modes, right? So with a small array, of course, if it's random, then everything is going to probably be unique, in which case everything is the most common element. But if you start to get larger, right, then, of course, now you start to distinguish things. 843 here appeared 5 times. If I run it again, 528 appeared 5 times. 0 appeared 6 times, right? And it's random each and every single time. It's uniformly random. That's why we're getting mostly 5s and 6 years. That's the count. Okay, great. It didn't take long at all, right? 1,000, 1,000. It's immediate. All right. Well, let's try 10,000. Okay, I noticed a little bit of a lag there, right? All right. Let's try 20,000. Even more of a lag, right? All right. Well, let's try 100,000. I wonder how long this will take. By the way, is 100,000 elements big data? No, that's ridiculous. That's 400K. That's 400,000 bytes. That's going to be less than 400K of data. Right? But it seems to be taking quite a while here. Right? So I'm going to go ahead and kill this. And let's go ahead and see if we can find a pattern here. The way that I'm going to try to find this pattern is by using a time operator. This time will allow you to run a program, and then it times it and reports how long it took. So a.out, let's start with 1,000. Right? In the real time, how long did it take? 0 minutes and 0.003 seconds. Okay? So let's go up to 2,000 here. And predict what should it be? I'm doubling the amount of integers that I have to check here, right? Okay, 0.01 seconds. All right, let's go up to, say, 10,000. Now, remember that it only took me 0.003 seconds for 1,000, and now I'm increasing that by a full factor of 10. Right? So how many seconds should it take now? About a half a second there, right? You said, let's see, it was 0.003 before, and this is about, what, 100 times slower, 150 times slower, right? Let's go ahead and go with 20,000. Right? So it went from a half a second to 1.5 seconds. What if I double it again? Go up to 40,000. So it went from half a second to almost, well, 0.49. We'll just go ahead and round it up to 2 seconds. So 0.445 up to 2 seconds. That's 4 times as big, right? Now, if I double it again, and it's 1.7, say 2 seconds, then if I'm right here and that it went up by a factor of 4, how many seconds should it take now? 8. Okay. Almost 8, almost exactly. If I went up to, let's double it again, to 80,000, how many seconds would it take now? We'll just round it up to 8. 4 times 8 is 32. Okay, we'll go ahead and keep that running there. Right? So why is this important, right? As you'll see this week, it's the difference between a program running like instantaneously versus a program that is going to take you 20,000, 30,000, 50,000, a billion years to run, right? There, 28. We're almost spot on here, right? Of course, the modulo, the amount of work that it takes to generate it, and it's not the only thing running on this system, etc. Is there a better way? Let me go. I'm not going to show it to you, but I will go ahead and. Yeah, I'll go ahead and get rid of this, and then I will uncomment this and int. Right? Now, there's a better solution here. Let's go ahead and try it for 80,000. Before it was taking 28.60 seconds. Instantaneous. Instantaneous. Let's try to break it. Let's go up to 1 million. 1, 2, 3. Almost instantaneous, 0.2 seconds now. Of course, it's going to take more time if I go from 1 million up to 2 million, right? It takes about double the time instead of 4 times as much time. I'm not sure where we got that 4 either. That was just experimental data, okay? I know where I got the 4. We'll talk about it later, right? But otherwise, let's go ahead and go back over here, and let's predict. Let's go back to the bad method here. What would it take for 2 million here? Well, remember 30 seconds was for 80,000? Is that right? It's good enough. Wolfram alpha. There we go. So if I go from 80,000 up to 1 million, 1 million, 1, 2, 3, divided by 80,000, that is a factor of 12.5. Right? So 12.5 times is big. Ignore this magic. 12.5 squared times, it took us 30 seconds before. Right, there we go. So that's the number of seconds it'll take us now. Seconds to minutes. I wonder how many minutes that is. So 78.13 minutes. How many is that? That's hours, right? So it'll take roughly 1.5 hours for this to execute over here. Right. What was it taking before? Less than a half a second. So we'll go ahead and let that run. It's not going to run within this class time, I can guarantee you. Right? All right, so this stuff is super important because it is necessary to look at this from an algorithmic standpoint. Even for small bits of data, and by the way, 2 million integers, that's still nothing. That is not big data. That is still small potatoes. All right? Being able to discern that this is a good algorithm and this is a bad algorithm without having to run it over and over and over again to see, oh yeah, that one executes instantaneously. That one would take, how many years would that take, right? Even being able to estimate that requires you to understand, to have at least a rudimentary idea of how these algorithms work. There are good searching and sorting algorithms. There are bad searching and sorting algorithms. Being able to discern between them and why is what makes a computer scientist, right? So let's take a look at our first searching algorithm. And it's called linear search. And we'll find out why here in a moment. Here's the basic idea. Given a collection of elements and a key element that I'll call K, search through the collection to find the element, find any element that matches K. Now, this is extremely vague, right? Did I make any reference to specific C stuff or to specific Java stuff? No. What is a collection? Well, in the context of C, what would be a collection? An array. In the context of Java, what could be a collection? An array or a list or a set or a map or any of those dynamic data structures that we were looking at. What elements? Are you always going to be holding integers? No, sometimes you're holding doubles. Sometimes you're holding student objects, film objects, airport objects, right? That you worked on with your last hack, right? So these are the details that you'd have to come up with when you implement this stuff. But this basic idea here of search through the haystack to find this needle, right? We're keeping that as abstract as possible. So again, what are you searching? An array, a list, a set, right? What is it a collection of? Integers, doubles, strings, airports, etc. Right? How are you searching? So if I just tell you to find a needle in the haystack, I didn't tell you that there were 50 needles in that haystack. I just said find one of them, right? You could find the first one. You could find the last one. You could find all of them. You could find the count for how many needles are in this haystack. How many fives are in this array, right? You could return true. Yeah, I found the needle, but I don't. You didn't ask where it was, so I can just tell you that it's in there. That's what you did on hack 7. Contains, right? So what are you searching? How are you searching, right? These are all questions that come up when you actually need to implement this stuff, right? Again, you could be searching for a particular element. You could be searching for the minimum. You could be searching for the maximum. Those are still search algorithms, right? More generally, right? You take an algorithmic perspective and design what is called pseudo code. Right? There we go. So what does pseudo mean? That prefix. A what? Not example code. This is kind of. Not real, false, fake, right? That's what it is, right? Pseudo code is fake code. It's not C code. It's not Java code. It's not Python code. It is, just this general outline of what to do. Okay. Let's go ahead and take a look at what pseudocode would look like for a linear search. We'll come back to this example here in a second. You clearly identify the input, and I'm just going to take the verbiage that we just developed. A collection, A, of elements, A1 through AN. Note here that it's not an array. And with arrays, and even with lists, we index based on 0. Why? Because that's how memories work. That's how memory in computers work. It's an offset. That index is an offset at the beginning of the array. The first element is at a 0 offset. The next element is at 4 bytes later if it's an integer, right? Etc. But this is the math way of doing it. And mathematicians don't like starting at 0. They like starting at 1. If you were ever indexing a summation or something in math, you would index it at 1. And a key, K. And my output here is going to be an element, A, in A, such that, did I say that these are integers, by the way? Nope. Did I say that what does equality mean in this case then?
The same.
The same, matches, right? I'm keeping it general. If they were integers, it would be equals equals in programming languages. If it were strings, this string and this string are the same if what? strcpy, they have the same contents. HELLO, HELLO. Or you could modify that. I don't care about the casing, right? Or I would say that these two strings are the same if they match the first 3 letters or something like that. You can put in different criteria here. I'm keeping it general and generic here with my pseudocode, my fake code. So all I need to do here is iterate over the elements in the array, or in the collection, excuse me. For each A in A, that's a bit Python-y, that's too Python-y, right? If you know any Python, the control structures always have this colon instead of an opening and closing curly bracket, right? I'm going to even stay away from that because I don't even want the hint that this is any particular programming language, right? So for each element A in A, if A is equal to K, according to whatever criteria that means, right? Then I will stop and output, not return because this is not a function, this is not a method. I'll output A. Ooh, cool, right? Vertical lines. There's no way to get that in a programming language. IDEs do it all the time. I don't know if it supports it over here, but certainly Eclipse does. And by the way, it's still going. So our estimate is probably going to end up being accurate there. But this is how I like to do pseudocode instead of opening and closing curly brackets, because there is no way that you can confuse that with a real programming language, right? There is no way that you can typeset this in any plain text ASCII situation. All right. So am I done with this algorithm? Are you always going to find what you're looking for? No. What happens if I go through every single element and none of them matches the key element? Okay, I could output an error. Like what? I could throw an exception. I could return some non-zero value, right? That's Java, that's C. This is more general, right? I'll just output phi. I'm just going to use Greek. That's the Greek letter phi. It's a stand-in. Phi, if no such element. Right? There's linear search. Why is it linear search? Because you go through each and every single one, right? So we have to understand that there's some cost to algorithms. There's some cost to running a program. You see this cost apparently right now, right? The cost here is time. This is going to take an hour and a half to execute. The cost to all those other things only took a half a second, or it was instantaneous, right? But everything was non-zero. Even the smallest amount, it took 0.003 seconds. So the cost here is time. How can I quantify that with respect to this generic pseudocode? So operations take time, right? Operations take time. The number of operations that you perform is proportional to the time it takes. If, for example, what would you want to focus on here? Give me an operation in this pseudocode right here. The comparison right there? Okay. That comparison right there. Right? Say that a comparison takes 5 nanoseconds. If I'd end up doing 10,000 comparisons, whatever 10,000 times 5 nanoseconds is, that's the amount of time that this thing is going to take, right? So it all comes down to how many operations does it perform? Question mark. Right. Well, let's take a particular example here. Now, we're no longer talking about general pseudocode. Now I'm talking about an actual array with integer values in it. If I were to implement this basic idea here on this array, what would it look like? You want to search for, say, I don't know, search for 102. Right? How many comparisons do I need to make in order to find it? Okay, so 1, 2, 3, 4, and then 5 in order to find, yep, that's the thing I'm looking for. 5. Okay. What if I searched instead for 0? 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. What if I searched for 80? Also 9. Why? You go through the entire array, you find that it's not in there, right? And return fee or return something, right? What about 42? 1. You find it immediately in the first place you looked, right? First place you looked, the last place you looked. Sometimes these things don't cost very much. You get lucky. Sometimes these things cost a lot. Sometimes these things cost, halfway between these other things, right? So, what's the cost here? What you end up doing is you end up focusing on one operation, and then you come up with an analysis, right? Before we do that, though, let's go ahead and come over here, and I'm going to kill this. I can guarantee you that it took already 24 minutes. Or sorry, 12 minutes, 12 and a half minutes. So I'll go ahead and kill that. And let's go ahead and touch search.h and touch search.c. There we go. And help me out here. Let's go ahead and actually implement this pseudocode over here with an actual C in actual C. Okay. So first of all, I'm going to have to write this this prototype. So I'll call it linear search. All right. And we'll go ahead and do this for integers. So how do I search an array of integers? Well, I need to give an array first of all. So what should I be passing in here? Int ARR. There's my array. Say what? Okay, const. Why? Because am I going to be making changes to the array? Nope. I'm just going to be looking through and seeing if I can find it. Is that an array though? Star, right? That would have then just been 1. If I pass in an array, what else do you need to tell the function? Size. And if you're searching for something, what are you going to have to do? Pass in that something, key, right? What should my return type be here? Void? Yeah, I found it, but I'm not going to tell you anything about it, about the results. All right. So what? Say what? Yeah, we have to return something. What are we going to return? An integer. Integer, what integer here, though? So I gave you, you're the function now. I gave you the key. You give it back to me. Does that help me? I want to know where's the element that you found, if you found it. The index. So let's put that in our documentation here. Searches the given array of integers of size n, right, for the given key value. Right? Returns an index, in fact, returns the first index at which it finds an element equal to the key. Okay, that's good enough for now. Let's come over here and implement it. No, I want search.c. There we go. So help me out. How do I translate this into C code? For loop for int I equals 0. This is the idiomatic for loop, right? For any array of size n. Oops. If the array sub I, the ith element, is equal to the key, I'm done, right? What do I return? Return I, the index at which you found it. Yeah. Well, okay, else. Should I put an else here and then return v? Right? So just because the first one is not the thing that you're looking for doesn't mean that the second one is not the thing that you're looking for. You have to go on, right? So there will be an else condition, right? But after the for loop, exactly. After the for loop, I return phi. Okay. Return phi. Is that real pseudo? Is that real C code? Nope. Return null? Can I return null here? Yeah, this is an integer. I don't return a pointer. This is not a pointer. Should I return 0? No, you didn't find it. False. That tells me that you found it at index 0. So what is a flag value indicating no such element exists in the context of C here? Negative? That would never be any valid array index, right? So we could use that as a flag value here. Put that in your documentation. Right? Returns -1 if no such element exists. Now think about doing this in Java. We're not going to because of time, but how would it look different? It would take an integer. It would take an array instead of an n. It would take maybe a list instead. It would still take a key. It would still have a basic for loop here. We could return -1. We could throw an exception. We could do a lot of other different things, which are all implementation details. Any one of those variations is going to be the exact same algorithm as we had up here. Any one of those variations is going to take a similar amount of time. If it took 5 minutes on an array of size 1 billion, it's still going to take 5 minutes or thereabouts proportionally in Java on a list of size 1 billion, right? Okay, great. That solves my problem for searching an array of integers. What about searching an array of students? Cut, paste. Searches the given array of students, structures of size n for the given key value. Okay. Returns the first index at which it finds an element equal to the key. Returns -1 if no such element exists. First of all, can I call it linear search anymore? Nope, it's a linear search for student. Okay. It doesn't take integers anymore. It takes a what? Student. And it returned, well, it still returned an index. Oh, I found Joe right there, right? But what would the implementation look like? Same exact for loop. Good. And instead of this criteria, I would end up comparing the two students. So a race of 0, how are you going to compare students here? Student is a first name, a last name, an NUID, a GPA, a class standing. That's how we designed it, right? So this student is equal to this student if what? Their IDs match. Okay, let's go with that. Right? So a race of I, that is a regular old structure. So do I use a dot or do I use an arrow here? Careful. So, as a reminder here, ARR is a student pointer, right, as declared up here. So when I index one of them, ARR sub I is a regular old student structure. Right? So how do I say pass it off to the print function, which expects a pointer to that one particular student? Array sub I with an ampersand in front of it turns it back into a pointer is again a student pointer. Right? Just a quick review there. I'll go ahead and leave that in the notes so you have it, but whatever. So this is a regular old student structure. Do I use the dot operator or the arrow operator? Dot. And you said NUID? Right? I think that was an integer, wasn't it not? Okay. So if that's equal to the key, and by the way, you should probably call it what? NUID if you want something like that. Right? Find the student with that particular NUID. If you don't find them, return -1. Great. Now I have a need to search for students, but not based on an NUID, if their last name and their first name match. I want to search students if their GPAs match. I want to find the student with the highest GPA. I want to find all students with lower than 2.0 GPA. Right? So what am I going to be doing if I take this strategy? I want to search for an array of doubles. I want to search for an array of floats. I want to search for blah, 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 blah. Copy, paste, change the type, but it's the same basic algorithm over and over and over and over. Should I follow this strategy of copy, pasta, copy, pasta, copy, pasta? Probably not. Right? There is a much better solution later that we'll look at later on. Okay? But for now, let's go ahead and note what we've done here. All right. So analysis. All right. A linear search algorithm performs a number of operations, and for us, our purposes, we'll focus on comparisons. Right? Performs, there we go. Sorry. So we can analyze this algorithm. It doesn't matter. It doesn't matter if we look at it from the perspective of the pseudocode. It doesn't matter if we look at it from this implementation or this implementation or the dozen or so other implementations that I just mentioned. They will all have the same performance, same general performance. Right? Let's go back over here and look at what we came up with. That sometimes we get lucky. Right? Sometimes we get unlucky. And sometimes we're right in the middle. So let's look at the times that we are lucky. Right? That's the best case scenario. Right? Best case scenario, how many comparisons do you make? How many comparisons can you get away with making? How few? One. Right? It takes one comparison. Finds it at index 0. All right, what's the worst case scenario? If there are n elements in it, n comparisons for an array or a collection of size n. And when does that happen? It is at index n-1, or it's an unsuccessful search. Okay. Can't always be the optimist. Can't always assume that the best case scenario will happen. Can't always be a pessimist either, though. Can't always assume that the worst case will happen. So what's a third way of looking at it? Average. So how can we find the average? Let's take the best plus the worst and average them. In other words, n plus 1 over 2. This is about n divided by 2. Forget about that plus 1. Right? In fact, it's just a plus half at the end. Forget about that. Can't make half comparisons anyway, right? You make one comparison or you make don't make a comparison. There's no such thing as a half a comparison. Right? So this is sometimes now this is just the hand wavy way of doing it. This is not the proper way of doing it. If you were actually to analyze linear search formally, you'd have to come up with a probability distribution on a successful search on each one of the indices, add that all up, a probability of an unsuccessful search, add that into the mix, blah, blah, blah. It's not that complicated, but guess what? You end up with the same answer. Right? So you just end up with the same answer properly. All right? We're not going to do that, though. So average case, you make about n divided by 2. Here, I'll do this frac n divided by 2. There we go. Hey, there we go. Comparisons. All right. So the average case and the worst case, are they that much different? Not that much. Let's think about this in terms of a graph. There we go. So here's the x-axis, here's the y-axis. What we're going to do with x-axis is this is the input size. The size of the array, or collection, whatever you want to look at it. So I'm going to rename that n. Okay? And I'm going to rename this t for, or time. And time is money, time is comparisons. Right? So for an input, what would it look like if I graphed out the worst case scenario? Where again, well, yeah, n comparisons. What's that going to look like? What kind of a line? A linear line. Right? Now that's why it's called linear search. What's it going to look like for the average case scenario? N divided by 2. Another line. There we go. It's just that is its slope any different? It's half as big. But what about the growth rate of this? Now this is generally we don't require calculus in this this course, and I'm not going to require it for like an exam or anything like that. But put on your calculus hats for a second and tell me, how do you quantify the growth rate of a function? It's what? It's first derivative. What's the first derivative of n?
1.
What's the first derivative of n divided by 2? 1/2. Right? But both of these are constants. Right? 1/2, 1, there's really no difference. Right? The growth rate is exactly the same. Both of these are linear functions. That coefficient sitting out front, 1, 1/2, it doesn't matter. Why doesn't it matter? Because we are quantifying the work here, comparisons. How many nanoseconds does one comparison take? On that computer over there, it takes 2 nanoseconds. On that computer over there, it takes 1 nanosecond. On that computer over there, it takes 50 nanoseconds because it's a terrible old computer, right? In other words, all of that quantification is just some constant sitting out front that we don't care about. C is going to be the number of nanoseconds that is required for one comparison, right? Move that over to a computer that's twice as fast. C goes down by 1/2. So does that mean that this 1/2 is important? No, because all you have to do is take it and incorporate it over here, and it's 4, right? It's still going to be a linear function, and that's why it's called linear search. Let's look at it from another perspective. What if I have an array of size n, and I kick that up to an array of size 2n? In other words, I double the size. I double the size. Over here, it took time t. How much time is it going to take now? 2t. Right? In other words, it doubles the time. What if I go from n to 10n? T before, it's going to be 10t. 10 times as much time. Right? Linear, linear, linear. Let's contrast that with our experiment over here that we were running, right, in this duplicates. Right? I'm just going to tell you right now that that's not linear. That is quadratic, exactly. And unfortunately, there's no way for me to draw a nice quadratic line there. N squared. Right? And by the way, is higher better or is lower better? Lower is better. Why? We are quantifying time. We are quantifying resources. Fewer resources is better. Right? More resources is worse. So let's compare this to a quadratic here. First, this is linear. What about a quadratic? So tell me what a quadratic function looks like. N squared. There could be lower order terms. N squared plus 5n minus 3. Forget about those lower order terms. When you look at the graph, as the size of the input grows, do those lower order terms matter? Not as much. Right? So n squared, that's, I'll just put that up here, sorry. Right? So suppose that I go from a size of n to 2n. Right? What happens to my time now? Remember that it's quadratic. It'll go from t to, remember it's quadratic, so 2t squared, which is equal to 4t squared. Right? Again, remember that the time is squared here. Right? So if I double the size, what happens to my multiplier over here? 4 times slower. That's where I got that 4 in the beginning. I knew that it was quadratic, and I knew that if I doubled the input size, right, I would end up getting a factor of 4 times slower. What if you went from n to 10n here? T squared becomes what? 100 times t squared, 100 times slower, right? So the better solution here that I demoed that took almost no time at all, it's not exactly linear, but it's almost as good, right? And that's why it took only a few less than 1 second versus 1.5 hours. Right? All right. Questions so far? No? All right, then can we do better? So let me go back over to the notes here. Can we do better? Yes, we can, using something called binary search. Right? So I don't know how much we'll get through today, but let me go ahead and try to give you the idea of what this looks like. When you get into Computer Science 2, Computer Science 3, courses start being labeled as data structures and algorithms, or data structures, right? Focus on that one word there, structure. Why do you like structure? There's order. There is, out of chaos comes, order. And so we like that. Why? Yeah, go ahead. Disorganized would be the opposite of structure. And so if it's organized, maybe we can exploit that organization. If it's disorder, right? If I just throw 52 card pickup. Everybody played that before? No? You never played 52 card pickup? All right, then we'll play it. I'll bring a deck of cards and you'll play it next time. The idea is that you tell somebody that's never heard of it before, you want to play 52 card pickup? Sure. And what do? You throw the cards in the air and say, pick them up. Right? So I'll throw the cards in the air and say, find me the ace of spades. Right? You'd have to go through that disorganization. Whereas if it were a brand new pack that was sorted, and the aces were the spade, spades were at the back, and it was sorted 2 through ace, what would you have to do? Here you go. Here's your card. Right? We can exploit that structure. So let's exploit that structure now. Whereas before we were searching through an array that was completely unordered, let's suppose now that we have an array that is instead sorted. Ignore the green for now. Right? We will use that in a second, though. Okay. Let's go ahead and search for, say, 2. Search for 2. Now, if this were a linear search, you'd start out at one end. That's not it. Oh, that's it. I got lucky. Right? If it were completely disorganized and you were unlucky, you'd have to go all the way maybe to the end or find that it didn't actually exist. All right? So how can I exploit this structure? The hint here is look at the middle. Right? Is 12 equal to the thing that I'm searching for? Nope. All right? But that tells me something. Tell me about everything down here. Since it's sorted, it is all less than 12. Tell me about everything over here. Since it's sorted, everything over here is greater than 12. Do I need to waste my time on this area at all? Nope. So I've effectively cut out half of the entire array. Let's do that again. I only have this part of the array now. Let's go ahead and jump to the middle there. 4. I'm searching for 2. That's not the thing that I'm looking for. So that's eliminated, just like this was eliminated. But what else is eliminated now? Everything above it. Right. Next iteration here, you can see that I'm doing this over and over again. Right? There. That is equal to 2. Done. Right. Let's do that again with another value. Sometimes you will get lucky. What if you search for 12? You jump right in the middle. It is equal. Done. Okay. Let's search for something that is not in there. Let's search for, say, 50. What does that kind of search look like? Well, there's the middle. It's not equal to 50. So we've eliminated it. But also, we've eliminated everything over there. Do that again. But now your middle over here is on the other side, 102. That's not the thing that I'm searching for. But I've also eliminated what? Everything over here. Next iteration, I'm now in, now what's the middle of 2? Well, right in the middle, but you can't do that. Right? So I'll suppose that this is the middle. Right? That's not equal to 50. But I've also, so I've eliminated it. And I've eliminated everything, here in this little empty slice. Next iteration, I find 42, and I find that that's not it either. And in which case, now I've got an array. I've zeroed in on it, right? If I'm keeping tabs of the left and the right, sometimes I come over here, sometimes I come over here, sometimes I come over here, until I'm down to one element. In that case, it was what? 42. That's not the thing I'm looking for. What happens to these, my 2 fingers then? I was moving them in, moving them in, moving them in. What happens? They go and pass each other. In which case I know that the array is now empty. The range of the array that I'm searching on is now empty. In which case I can say certainly that there is no such element. Okay? That's called binary search. Let's go ahead and implement it. Right. There's linear search. We'll do it the same thing here, but for, oops. Not linear search, but binary search. Why is it called binary search? Cuts it in half, right? Binary is 2, right? Ternary, there is ternary search. You can cut it into 3 parts. There's quaternary search. You don't want to consider anything beyond binary search because it's all the same. Right? All right, so let's think about binary search. How am I going to implement this? I'm certainly going to take an array. I'm certainly going to take a key here. But what else should I take? So let's think back over here, and let's think more generally. There we go. There's the array, initially. So you start at index 1 all the way up to index n. You jump into the middle here, right? N divided by 2. But now let's go ahead and consider a more general way of looking at this. Instead of looking at particular index values, let's look at a sub, oops, it's too thick now. A sub L, L being my left index, and A sub R, R being my right index. So eventually they're left and right are going to be updated, updated, updated. Here's my new array, or my new sub-array, right? Hand that off to another function. You go ahead and find it, right? Okay, well, I didn't find it. It's not the middle element, but here's the next part that you should search for. Give it off to another function. Say, search for that part, search that part, search that part. What does that sound like to you? Recursion. Let's go ahead and implement this in a recursive fashion, and then we'll come back and fix it so that there's no recursion, right? I'm going to pass in not the size of an array, but the left index and a right index. Initially, it's going to be 0 and n minus 1, but as it gets updated and I make a recursive call, recursive call, recursive call, eventually they're going to pass, right? At which case, that's your base case. You didn't find it, okay? Let's go ahead and implement this over here, and then we'll also have to test it eventually. There we go. So, take care of, corner cases, error handling if the array is negative, or if the array is null, return. If the left or the right, whatever, or beyond, whatever else you can come up with there. Let's go ahead and think of our base case. The array range is empty. Right? Left, right, left, right, left, right. When is it empty? When they're equal, though, you could have been searching for 42, right? And you want to make sure that you check that. So when they've passed, you know that there is no such element. So if left is greater than right, this is an unsuccessful search. Let's go ahead and return what? Well, what do we return above? -1. Else. Now, there are a couple of cases here. Now, what we could do is, let's go back over here. What we could do is, first of all, we need the middle element here, right? What is M? What is the index of the middle element? In general, if we've got left and right. How do I get, left is over here, right is over here. How do I get that middle guy? N minus 1 over 2 on the first iteration, right? But then you index, you index, you index. Here's a range, right? There are 10 elements in here, and the index starts at left. So I would need left plus 5 or so. I could go right minus left. That'll give me the range, right? Then divide that by 2 to get exactly half over. But then you start at L, so you need something like that. That's the proper way to do it. Let's just go ahead and do a quick and dirty way of doing this. If I have a number line here, X, and I've got A and, I'll go ahead and go with L and R. What's that middle element right there on the number line? L plus R over 2. Why? What is that? That's the average. So L plus R over 2. Don't do that in practice. If you're wondering why, it's because it's susceptible to overflow. Don't try that at home. Do it proper, the way that you suggested. L plus L minus R over 2, right? And that will not be subject to overflow, right? But I'm just looking for a quick demo here. So let's compute the middle index here. Int m is equal to L plus r all over 2. We're doing integer division. What should I be wary of? Truncation. So 10 plus 30, or 10 plus 20 divided by 2, that's 15, that's fine. 11 plus 20 is 31 divided by 2. That sounds like it should be 15.5. Is 15.5 any index that you ever heard of? Nope. But it's okay. Why? Truncation takes us back down to 15, and we're back at a valid index. Right? That's my middle index. So now let's take a stock of what we did here over here. Right? So if, here's m, m, a sub m. If this is the thing that we're looking for, we're done. We don't need to recurse anymore, right? So let's check for that first. If a sub m is equal to the key that we're searching for, we're done. We return what? M, the index at which you found it. Else, if the thing that you're searching for, key, is less than a sub m, then where am I going to search? Am I going to search in the left, or am I going to search in the right? The thing that I'm searching for, k, is less than this thing right here. So I search in the left. Search in the left part. Else if, now you don't, strictly speaking, you don't need an if here, but I'm going to drive home the point of what we're doing. If the key that we're searching for is greater than that middle element that we just looked at, then I'll search in the right part. There. There. Okay. How do I search in the left part? Okay, so you said change the right, right? Oh, do I change L to get this part right here? Nope. I change R to be what? Do I change it to be M? -1. Why? I already looked at M, right? So I make a recursive call to binary search on the same array. I didn't change it. In fact, I can't because it's const. The left is unchanged, but the right is now m-1. And am I changing the key? Nope. So I search in the right part. What gets updated now? Array is unchanged. The left becomes what? m+1 to get onto the other side of m. The right is unchanged. The key is unchanged. And, of course, you do need to return these computations here. And again, strictly speaking, this if is not necessary because it's either equal, less, or greater. Right? There's no fourth way there. Right? So you could get by with just this, but I'm going to leave it there to drive home the point that you are searching, the key is greater, therefore you need to search on the right part. Okay? Copy. Main demo here, and ignore. Yes, I want it overridden. Okay, ignore all this film stuff. There we go. Ignore film. Right, there we go. And I called it binary search, right? All right, so gcc demo.c and search.c. Hopefully there's not a compiler error here, but there is. All right. Oh, okay, what was wrong? L, R, A, right? Let's come back over here. L should be what? Left. R should be right. Right. A should be ARR, but I'll just go ahead and change it up there. So I guess I have to change it down here then too. Right. All right, that's good. Now let's go ahead and get rid of that student stuff because, for now, because we don't actually have any students in here. There we go. Come on. Get rid of this for now. I just want to demonstrate the other two. There we go. All right. So before we run this, let's understand what's going on here. Okay. And in fact, I'm going to restore this. Ignore this for a second. All right. There we go. So I've got the same array of numbers that we started out with, 42, 4, 9, etc. That it's not sorted, and I'm going to try to search for 42 here, using that linear search that we designed. Let's see if it actually works. And we should find it where, by the way? At index 0. If we search for 102, where should we find that? 0, 1, 2, 3, 4. Excellent, it works. Now, what happens when we do binary search? Okay, GCC. We should still find it at index 4, right? I'm still searching for 102 right now. Ah, success. What if I search for 42? Index -1. Linear search successfully found it at index 0. Why did binary search fail here? Because it's not what? Organized. It's not organized, and we call that sorted. So in other words, in order to use binary search, to exploit that structure of looking at the middle element and then cutting it in half each and every single time, we have to have it sorted, which is what we're going to do starting on Thursday. All right. A dot out. Now it works. All right. Of course, you would need to go through and rigorously test this. Yeah.
So, say we designed our own sorting algorithm, would it have to be logarithmic as well as the binary search in order to
I'm going to show you. Don't sort. Don't roll your own is going to be our motto here. Don't design your own sorting algorithm. Use what's built in. Sorting algorithms are going to either be good, order n log n, which is quick sort, merge sort, stuff like that, or bad, insertion sort, selection sort, quadratic. All right, and there's no hope of if you want to roll your own implementation of quick sort, great, go ahead as an exercise. But at the end of the day, you don't want to do that. Instead, what I did, you're going to want to do what I did up here. Where's the better, most common? There we go. Better. QSort. It's part of the standard library. Every language is going to have some sorting built into it.
Well, so then, if you did both the sort and the binary,
You have to do the sort first, and then you can exploit binary search. Exactly.
is that still faster than a linear search?
Oh yeah. Well, I take that. But if you're only going to do one search, probably not. But if you're going to do multiple searches afterwards, right? Then yeah, it's going to be a hell of a lot faster. Again, it's going to be the difference between 1.5 hours and a half a second, right? Especially on the project when that comes up, right? Okay, let's do some analysis here. And again, it's not going to be a formal analysis. I'm just going to show you how it works, right? So you start out with a size of what? N, right? And you make one comparison, and if you get lucky, right, it's the middle element and you're done. Right? Otherwise, that cuts it down to a size of n divided by 2, right? You make one more comparison, and either that's the thing that you're searching for, or again, you've cut it in half to n divided by 4. Make another comparison, and that cuts it down into n divided by 8. And you start to see the pattern here. It's going to make one more comparison. It cuts it down to n divided by what? 16, dot, dot, dot. Come back up over here, dot, dot, dot. What I'm doing is I'm cutting it in half every single time. N divided by 2 to the k. Right? And I'd made one comparison for each one of these things. Right? One comparison, and then dot, dot, dot. Eventually, you get down to an array of size what? For an unsuccessful search, let's say. Worst case scenario. 0. Unfortunately, that's not going to let the math work out. So let's go ahead and say that once you get down to an array of size 1, then the next iteration, you don't do any comparisons at all, right? Because, let's go back to over here to linear binary search. Right? You just find that the left and the right have gone past each other. There's no comparisons done here at all. It's an unsuccessful search, you immediately return. Okay? So eventually you get down to an array of size 1. So how many iterations did you do? I did 1, 2, 3, 4, dot, dot, dot. How many is that? N divided by 2 to the k is equal to 1 for what k? Right. You did k iterations because you cut it in half once, twice, thrice, twice. What is the fourth version of that? I don't know. And then k times until you got it down to 1 here. Solve for k for me. That's easy. Take it to the other side. How do I get k alone there? Log base 2 of n is equal to, when I take the log base 2 of 2 to the k, what happens? To the k. Good. All right, so what is k? Log base 2 of n. Now, we're self-respecting computer scientists here, so anytime that we write log without an explicit base, what do we mean? 2. Right? Mathematicians like base what? Oh, really? Calculus mathematicians like what? Base natural log, and the base of the natural log is what? E. Oops. Base E. 2.71, blah, 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 blah. What the hell is so natural about 2.71? 10 is natural, right? Because we're humans, and at least the luckiest of us have 10 fingers and 10 toes, right? So ours is natural base 10 because we use 0 through 9, Arabic numerals. Who uses base 2.71? Can you even imagine a base that uses 2.71 characters in their counting? No, but you can do it, at least theoretically. Right? So what is natural about base E? Again, put on your calculus hats and tell me. The first derivative of E is what? E to the x is equal to E to the x. In other words, this constant coefficient out here is 1. For any other base, there ends up being a natural log of 2. That's the change of base formula that's playing a role there. Right? So mathematicians say that this is natural because of the first derivative. It's the magic number at which the first derivative gives you a constant coefficient of 1, and it goes away so that you don't have to worry about it. Right? Of course, we as normal humans would say 10, but we as self-respecting computer scientists view everything in binary zeros and ones, and therefore implicitly it's always going to be base 2. How much better is that? Remember that linear search performs n, we'll just go with the worst case scenario here, comparisons. Binary search only does log n comparisons. So if you want to, go ahead and map these out. Right? What does that n look like? Nice linear function up here. What does that log n look like? If you zoom in on it, it looks like this, right? But at this scale, when you're comparing it to a linear function, what does it look like? It's essentially flat, right? So this is n, this is log n. Right? That's one way of looking at it, right? What's another way of looking at it? If I go from, like what we did last time here, n to 2n, right? Then linear search is going to end up being t to 2t. But if I go from n to 2n for log of n becomes what? If you double the input size, log of 2n, don't get ahead of me, right? Now pull out your log. Now take off your calculus hat and put on your pre-algebra hat, or maybe your algebra hat, and tell me your log identities here. Log of AB is equal to what?
Log A plus 1.
Log B. So this becomes n, or sorry, log n plus log 2. I just switched them around there because that second one is equal to what? 1. So in other words, if you go from 1 million to 2 million, you will end up doing 1 million more comparisons. If you go from 1 million to 2 million over here, you'll end up only doing not 1 million more comparisons, just one more comparison than you were doing before. One more comparison versus 1 million more comparisons. Which one of those is better? One, obviously. Right? And that's the difference between getting something done in a half a second versus getting something done in 1.5 hours, right? Even for small amounts. Yeah.
Is like binary the most typical sort of thing?
Yeah, I mean that's but you have to make the investment. You have to sort it first, then you can exploit binary search. But once you've sorted it, or even better, you maintain a sort. And this is how databases do it, for example. They don't put stuff in and then, oh, I'll resort it. Oh, we've got a new element here. I'll just go ahead and throw it in at a random location, resort the entire thing. No, put it where? Where it belongs, so that you have a maintenance of a sort there. Right? So this is actually, the difference between these two things is actually exponential, right? That the logarithms are exponentially faster than linear functions. Right? Again, you pull out your calculus out and tell me really quickly here, since it's not calculus, what is the first derivative of n? What was it? 1. In other words, its growth rate is constant. What is the first derivative of log n? Oh, sorry.
It's like 1 over n plus a time the constant.
1 over n times some constant, which involves the change of base formula. So in other words, a growth rate of a constant growth rate, or characterize that growth rate as n tends towards infinity. 0, well, it'll converge onto 0, right? In other words, the growth rate itself is getting smaller and smaller and smaller, right? That's why it's plateauing here. Of course, it's monotone increasing. It will not converge to any value, but the growth rate, the tangent function, right? The tangent line will get not steeper. What's the opposite of steep? Shallow? Shallower? Do you say that? All right, shallower and shallower and shallower, right? So every tool that you can bring to bear on this, algebra, calculus, tells you that these two things are different, and definitely this one is preferred. In case just running it wasn't enough. Half second versus 1.5 hours. All right, so next time we will look at a better version of binary search, and then we'll move on to that investment. You have to have it sorted first or it doesn't work. Okay? See you then.